RLC circuits are fundamental building blocks in the world of electronics. They are essential components found in a wide range of devices we use every day. RLC stands for resistor, R, inductor, L, and capacitor, C. These three passive components, when connected in various configurations, create circuits capable of filtering, tuning, and oscillating electrical signals. Imagine an RLC circuit as a kind of electrical playground. Resistors act like friction, slowing down the flow of electrical current. Inductors, on the other hand, resist changes in current, like a heavy object resisting a change in motion. Capacitors, like small reservoirs, store electrical energy and release it when needed. These components, when combined, exhibit fascinating behaviors. They can resonate at specific frequencies, similar to how a tuning fork vibrates at a particular pitch. This resonant behavior is what makes RLC circuits so versatile and widely used in various applications. From radios and televisions to smartphones and medical equipment, RLC circuits play a crucial role in shaping our technological landscape. Understanding how these circuits work is key to comprehending the inner workings of many electronic devices we rely on daily. Resistors are the simplest of the three components in an RLC circuit. They are designed to impede the flow of electrical current, much like a narrow passage restricts the flow of water in a pipe. The amount of resistance a resistor offers is measured in ohms, omega. Think of a resistor as an obstacle course for electrons. As electrons try to flow through the resistor, they collide with atoms within the material, making it harder for them to pass. This resistance converts some electrical energy into heat, a phenomenon we experience in our daily lives, such as the warmth generated by an electric heater. Resistors are essential for controlling current levels in circuits. By selecting resistors with appropriate resistance values, engineers can ensure that the right amount of current flows through different parts of a circuit, protecting sensitive components and optimizing performance. Without resistors, electrical circuits would be like runaway trains, with current flowing uncontrollably. Resistors act as the brakes, providing stability and predictability to the flow of electricity. Inductors, often coiled wires, possess the intriguing ability to store energy in magnetic fields. Unlike resistors, which resist the flow of current, inductors oppose changes in current. When current flows through an inductor, it creates a magnetic field around it. Imagine an inductor as a heavy flywheel. Just as a flywheel resists changes in rotational speed, an inductor resists changes in current flow. When current tries to increase or decrease, the inductor's magnetic field either expands or collapses, opposing the change. The unit of inductance is the Henry H. The higher the inductance, the stronger the inductor's opposition to changes in current. This property makes inductors invaluable in circuits where smoothing out current fluctuations is crucial, such as power supplies. Inductors are also used in filters, which selectively allow or block specific frequencies. By combining inductors with capacitors, engineers can create circuits that resonate at specific frequencies, forming the basis for radio tuning circuits. Section 4. Demystifying capacitors' electric energy storehouses. Capacitors, unlike inductors that store energy in magnetic fields, store energy in electric fields. They consist of two conductive plates separated by an insulating material called a dielectric. When a voltage is applied across the plates, an electric field builds up, storing energy. Think of a capacitor as a tiny rechargeable battery. When connected to a voltage source, it charges up, storing electrical energy. When the voltage is removed, the capacitor discharges, releasing the stored energy. The unit of capacitance is the farad. The larger the capacitance, the more electrical energy the capacitor can store. Capacitors are essential for filtering, smoothing, and timing applications in electronic circuits. In power supplies, capacitors help to smooth out voltage ripples, providing a stable DC output. In timing circuits, capacitors can be used to create time delays like the pause between flashes in a camera flash. Section 5. The synergy of RLC components, a dynamic interplay. In an RLC circuit, resistors, inductors, and capacitors work together in a fascinating interplay of energy storage and dissipation. The behavior of the circuit depends on the values of these components and how they are connected. When a voltage is applied to an RLC circuit, the capacitor begins to charge, and current starts to flow through the inductor. The inductor resists the change in current, while the resistor limits the overall current flow. As the capacitor charges, the voltage across it increases, eventually reaching a point where the current through the inductor starts to decrease. However, the inductor's magnetic field now starts to collapse, inducing a current that tries to keep flowing. This interplay between the capacitor's electric field and the inductor's magnetic field creates oscillations. The energy sloshes back and forth between the capacitor and the inductor, with the resistor gradually dissipating the energy as heat. Section 6. Resonance. When RLC circuits find their rhythm. One of the most remarkable properties of RLC circuits is their ability to resonate at specific frequencies. Resonance occurs when the energy stored in the capacitor and inductor oscillates back and forth at its natural frequency. Imagine pushing a child on a swing. If you push at the swing's natural frequency, even small pushes will make the swing go higher and higher. Similarly, in an RLC circuit, when the frequency of an applied voltage matches the circuit's resonant frequency, the circuit's response is maximized. At resonance, the impedance of the circuit is minimized, meaning the circuit offers the least opposition to the flow of current. This property is exploited in various applications, such as radio tuning circuits, where RLC circuits are used to select specific frequencies from a range of radio waves. Section 7. Real-world applications of RLC circuits. RLC circuits, with their ability to filter, tune, and oscillate, find applications in a vast array of electronic devices we encounter every day. Radio receivers. RLC circuits are the heart of radio tuning circuits, allowing us to select specific radio stations by adjusting the resonant frequency of the circuit. Televisions. Similar to radios, televisions use RLC circuits in their tuning circuits to select specific channels. Wireless communication. From smartphones to Wi-Fi routers, RLC circuits are used in oscillators and filters that generate and process high-frequency signals for wireless communication. Medical equipment. RLC circuits are found in various medical devices, such as MRI machines, which use resonant circuits to generate strong magnetic fields for imaging. Power supplies. RLC circuits are used in power supplies to filter out unwanted noise and ripples, providing a stable DC voltage output. These are just a few examples of the countless applications of RLC circuits. Their versatility and ability to manipulate electrical signals make them indispensable components in modern electronics.